Mr. Roshan Tiwari from ISA Kolkata with a talk, Self-Replication and Out of Equilibrium Phenomenon, the Basis of Life, followed by later Dr. Vignesh Krishnan Kuti, right, from Singapore. So first, let me introduce Mr. Roshan Tiwari. Mr. Roshan Tiwari is a research scholar in the Department of Physical Sciences at the Indian Institute of Science, Education and Research, ISA, Kolkata. He completed his Bachelor's in Science in Physics from the Banaras Hindu University, BHU at Varanasi in 2014, and he's currently pursuing his integrated PhD at ISA, Kolkata. His current research interests include spectroscopy, bio-inspired waveguides, microscopy, sensing, optical trapping, and statistical analysis. He is enthusiastic about learning and disseminating science to the masses through outreach talks and experimental demonstrations. Moreover, he is interested in delving deeper into the unexplored aspects of reality with possible connections with age-old wisdom. So it gives me great pleasure now to hand over the screen on the stage to Mr. Roshan Tiwari. Sir.
So first of all, good evening and respected all seniors and all my dear friends. So I am Roshan Tiwari from. I'm doing my finally. I'm in my final year PhD student PhD, and I'm really thankful to Bhaktivedanta Institute for giving me such an opportunity to present my views on what is the basis of life. So so today I am going to present a work on life from the perspective of physics, that is especially thermodynamics. So today my topic is self-replication and out of equilibrium phenomena, the basis of life. So before that, I would like to pay my humble obeisances to my spiritual master who have guided me in every aspect of my life. So So now this is my general outline for my today's talk. It will be including time reversal symmetry. The people will come to know about what it is, and then detailed balance equations, and then breaking of this time reversal symmetry, irreversibility, entropy production, probability. Then we will do some modeling of self-replicator, and then bacterial self-division modeling. So every time we used to heard about what is life, a many book has been written, and even Schrodinger has tried to explain in terms of his perspective. But most of the definitions of life is based upon operational definitions. For example, about the difference between living and non-living thing. For example, living has complexity and organization, whereas non-living thing doesn't have. Maybe it has some sorts of crystals have organization, and these organizations, the living beings are highly organized in terms of they have very spatial coordinated parts, and they used to do a very coordinated working also. For example, a single cell, even a single cell has that sort of this type of organization. Then they have energy metabolism. For example, they exchanges energy and matter from the surrounding. So this is a very complex reactions. There are a lot of biochemical reactions happening inside the cell, inside the body of a living being. And then they used to grow and reproduce. Growth means the accumulations of cell in some order, and reproduction also, like our all these previous speakers have told about. And they also respond to stimuli. Means any changes which is happening, they used to respond it. For example, we remove our hand when we used to touch a very warm water or something like that. And the adaptation. So they adapt to changing environment. So here I have given examples of a living organism. Here it is an insect called beetle. Okay, and here it is a robot, insect robot, which has been designed by in US, and it runs on methanol. So it has some degree of freedom. It just moves. Okay, but it doesn't. It cannot reproduce. It cannot grow. It cannot adapt. But here, the life, the living of beetle can do all these things. So these things, all these things, make it different from any non-living. So this self-replication is very important term, and it is very much unique to living organism. But now some research is also going on where they are trying to replicate in non-living things also. So, as you know, I have a title called self-replication. So, self-replication is basically here it is a very nice uh, file where you can see the E. coli bacteria is dividing and self-replicating. So, what this self-replication is, it means that every living organism has the potential to replicate or make a copy of itself by exchanging energy and matter with its surrounding, for example, cell division. But reverting back the process of self-replication is very, very unlikely. I have never seen any bacteria becoming one from two. Okay. So some sorts of, from physics point of view, this self-replication process is constrained by thermodynamic laws. For example, irreversibility. It has been very much researched in thermodynamics about this irreversibility. Why there is a one way. Okay. So let us just learn about simple concepts in thermodynamics, that what is reversible process, as many of our participants know about this, that returning back of a system from final to initial state. And water equilibrium process, when the rate of forward and backward reaction becomes equal, then they are called equilibrium process. And what is irreversible process, when the system cannot retrace back to its original position, original state, then it is irreversible process. So in irreversible process, systems are mostly in non-equilibrium state. And this irreversible process you can see everywhere in your surroundings. Any chemical reaction, even your growth, even your aging is also a irreversible process. So this irreversible process is guided by some sorts of second law of thermodynamics. So I am giving examples of an irreversible process where you can see the rusting is happening of an iron. So the rusting is an oxidation process, and it is very slow. It takes some time. It takes some long time to rust some iron. But in case of burning, burning is also an oxidation reaction. It takes few seconds to burn something. So the rate is very important parameter here. So in the same way, our aging, we are also getting age. I have never seen some aged person becoming child. So there is a arrow of time in some particular direction. It doesn't retrace back. So what guides this type of one way, that we have to understand, is thermodynamics responsible for that or something else? So before that, let us introduce ourselves to time reversal symmetry. So in Newton's equations, in dynamical laws, we know that there is a time reversal symmetry. If you reverse the momentum, we can run back along the same path in time reverse order. That is, any rewind movie is physically possible. If you make a movie and rewind it in a backward direction, that is also a possible solution. So there is another example, very fine examples of a plant. You can see in the two uh, files that a plant is growing in forward direction, and in the second file you can see the plant is uh, growing back. It is decaying back to its original seed. So from our common experience, we have never seen such type of things, that plant is going back to its seed. Okay, so for example, this plant is growing back to its seed, and then it is releasing all the sunlight. It never happens. It takes sunlight, the seed grows and grows and grows, when we become plant. Okay, so here the important thing is that in this video we have focused on the plant, but we are not focusing on the surrounding. Surrounding is also playing a huge role. There is an exchange of matter, energy taking place between the system and surrounding. Okay, so surround this a lot of heat is there in the atmosphere, a lot of particles is there in the atmosphere. So what is happening? The plant is releasing the energy. And so the question is this time reversal symmetry is breaking? And then what is responsible for this time reversal symmetry? We have never seen the plant going back. So there is a symmetry breaking happening. So I have made one simulation. Maybe it would be very explanatory for people. So you can see here a man is jumping from this barrier, jumping back and forth. But here another person standing, and there is a huge barrier out here. So now he is using some jet and jumping from that jet, using that jet, and now his fuel is over. So now he doesn't have fuel now anymore. So now My question is, can he use his heat which is lost in the atmosphere back and use it to reverse back? It is not possible because the heat which is lost. It can never be it can never be attained back. So there is some sorts of symmetry breaking happening because the heat which is lost, we cannot take it back. So the conclusion somehow is breaking of time reversal symmetry is linked to entropy production because the uh, system, the entire surroundings entropy has increased. Okay, so there is a very nice paper on it published in PRL in 2007, entropy production and time asymmetry in non-equilibrium fluctuations. Those who are interested can read this paper. So now let us understand it in more empirical way. So in equilibrium process, what happened? There is a three states A, B, and C. So from going from A to B, the rate of going from A to B is equal to rate from B to A. Okay. So the rate is equal. Similarly, going from A to C and C to A are both equal. Okay. But in non-equilibrium process, what happened? The state, the probability of going from A to B and coming back to B to A is not same. Similarly, B to C and C to A are not same. So there is a net flow of anything you can say the matter, the energy is there. So that is a non-equilibrium process. And it is very common in our day-to-day life. Everywhere we see a non-equilibrium process. Like in our own body, the blood which is pumping in the artery. Okay, so it is driving by some external agents from our like our heart. Our heart pumps. Okay. Similarly, if some driving force is there, or either some loss is there, you can say the rate is not equal, then it is going to become a non-equilibrium process. So let us understand it more mathematically using some master equation. So I have so what is master equation? So it is used to describe the time evolution of a system that can be modeled as being in a probabilistic combination of states at any given time, and the switching between states is determined by a transition probability matrix. So let me give you an example. There is a three state A, B, and C. Okay. So probability of coming from going from A to C is 0.9 and going back to C to A is zero point 0.5. So you can see there is a point. Let us take examples of going from A to A. So A to A is 0. There is no probability. So similarly, A to B is zero point 0.1. Okay. A to C is zero point 0.9. So I have written it in a matrix form. So transition probabilities can be written in a matrix form. So the rate of change of probability similarly can be quantified into the product of the probability of state into the transition probability matrix. So this is a very important formula and it is used in various statistical mechanisms. So now, if the rate of change of forward direction is equal to backward direction, then it is going to be called detailed balance equation, and this is a state of equilibrium system. This you can see it's a Boltzmann distribution e to power minus beta ei by z beta. So it is a the same let me yeah, so it is the product of transition probability matrix and this is the pi, the probability of a state. Okay, so going from I to j and j to I backward is same. Okay, so but what if a process is not in equilibrium, then what will happen? The ratio of the forward and backward direction would be the entropy production, the change in the entropy of the path. Okay, so this is the very important relation. So above equation sets up a microscopically detailed relationship between the irreversibility of a transition and the amount of entropy is increased in the surrounding over the course of forward trajectory. So the entropy production is very important to make some process irreversible. So similarly, if we don't have a discrete state, but if we have a continuous microstate which is evolving in time, then we can denote a trajectory. Okay, and this is the same relation which we have derived for now for continuous variables in time t. And the probability for backward and forward trajectory is going to be the heat release. So now, as we all know that for a spontaneous process, the entropy change of the universe is positive. And the change in the entropy of the system plus the change in the entropy of the path must be greater than and equal to 0. So using a very heuristic derivation, we have derived a extended second law of thermodynamics. So you know this and these portions, but we have introduced this second this another term which is called the irreversibility term. Okay, this is a very important term because why? Because this is a called Crookes relation. And using Crookes microscopic relations, the macroscopic irreversibility of a transition from an arbitrary ensemble of states to a future ensemble state sets a stricter boundary on the associated entropy production. So initially, there was no as such stricter boundary production, but because of this irreversibility, we have put a stricter set of boundary conditions over the entropy production. So we can say, so the more irreversible the macro process is, the more negative is going to be this ln, this term, and the more positive must be the minimum total entropy production. So for example, initially the entropy production bound was zero for equilibrium process, but now if this process is becoming more and more negative, then it is going to shift to the right hand side of that equation, and it will become a non-zero and it will set a different boundary. So now we are going to model our replicator. So suppose there is a simple self-replicator living at an initial temperature beta, both population and much greater than 1, obeys a master equation of the form. So this is a master equations. And you can go through it, you can learn it how to derive master equation for any simple self-replicator, where P and T is the probability of having a population of n at time t, and G and del is greater than 0. G means the growth rate parameter, and del is the decaying parameter. Here, del amounts to a reversion of the replicator back into exact set of reactants in its environment out of which it was made. So here, G is the growth parameter and del is the decaying parameter, and you could derive it simply in order to get the master equation of a self-replicator. So now what we have did, we have used again this extended as a second law and for that self-replicator thing. And in case of this forward backward reaction and this forward reaction, we have put this growth term and decaying term because this same thing. So it is going to be putting a bound on that entire entropy production. So here it is called fueling del Q. 1 by del is durability. Okay, so inverse of decaying is durability. More decay, less durable anything. For example, in our daily life, we heard about durability of something. Battery is more durable, means it has more lifetime. Similarly, order, entropy, this internal energy of entropy change of any internal system lead less entropy change, more and order would be there. Okay, similarly, G is the for growth rate. So this is the general equation which we have derived from this extended second law. So in order for the self-replicator to be capable of net growth, we have to require that G must be greater than del, which in turn sets a positive lower bound on the total entropy production associated with self-replication. So this is going to put a positive lower bound. So now we have arranged our equation in such a way that we have made it in terms of del Q, del Sn. So our main variable, like here, we want to express everything in terms of growth. So now the conclusion which we came to find that the maximum net growth rate of a self-replicator is fixed by three things. Maximum net growth rate, that is Gmax, which depends upon internal entropy, durability, and heat dissipated into the surrounding bath during the process of self-replication. So what is the conclusion? So for example, if you have two different replicator with fixed internal entropy change and durability, that have different heat values, for example, del Q and del Q dash. And if del Q is is greater than del Q dash, then clearly from the equation, G max dash is going to be greater than G max. G max is greater than G max dash. What it means that the replicator that dissipates more heat has the potential to grow faster. So for example, if a replicator is dissipating more heat, then its growth rate is going to be more. So what it really signifies? So uh, yeah, so it's a more growth rate means it means that if something is exhausting more heat, then it has more growth rate. It is similar to like our Darwin's fitness, like he says, like yeah. So if a organism has more metabolism, then it has more degree of fitness and it has the more chance of survival. So it is similar to like that. So we have derived it thermodynamically. So so similarly, self-replicator can increase their maximum potential growth rates not only by more effectively fueling their growth through del Q, but also by lowering the cost of their growth through del and order through del SN. What it means? It means that the less durable or less organized the self-replicator is, the less metabolic energy it must harvest at minimum in order to achieve a certain growth. So less durable, if a self-replicator is very less durable and less organized, then it has to undergo less metabolic energy to attain a certain growth rate. Okay. And at the same time, if a self-replicator is very high durability, very highly organized, then for the same growth rate, it has to expand more metabolic energy. So, thus, in a competition among self-replicator to dominate the population of the future, one strategy for success is to be simpler in construction and more prone to spontaneous degradation. So, this is the key of success. Such that if they are more prone to spontaneous degradation, then they have the high capacity to grow. They can evolve. So the empirical and biological fact that the reproductive fitness is intimately linked to efficient metabolism has a clear and simple basis in physics. So now let us take examples of self-replicating polynucleotides. We have model self-replicators, but what about polynucleotides? They are also self-replicators. They are in our body, for example, DNA, RNA. So using the above equations of extended second law, can we demonstrate the role of durability in replication fitness? For example, uh, we know that DNA has more durability, it has more uh, bonds in comparison to one another. So let us compare it. So from the above equation, we have already know this one. The heat bound is equal to a ratio of G by del, and we have neglected the internal entropy change. And this is our extended second law. So heat bound for RNA is going to be this one. So growth rate is 4 year and del is 1 hour, and it is coming as 7 kilocalorie per mole. And the enthalpy for the reaction is in the vicinity of 10 kilocalorie per mole. So it is very, very near to this one. So RNA molecule operates quite near the limit of thermodynamic efficiency. What about heat bound for DNA? So for heat bound for DNA, the growth rate is about 3 into 10 power 7 years, and it is coming about 16 kilocalorie per mole. So this exceeds the estimated enthalpy for the ligation reaction and is therefore prohibited thermodynamically. So the heat bound is so much that it is almost prohibited thermodynamically. So the far greater durability of DNA demands that a much higher per base thermodynamic cost be paid in entropy production in order for the growth rate to match that of RNA. So the RNA growth rate, to match with RNA growth rate, DNA has to invest more and more energy. So this observation tells us that RNA and not the DNA must have acted as the material for the prebiotic emergence of self-replicating nucleic acids. So many hypotheses are there, RNA world hypothesis, where they say that RNA are more responsible for life and prebiotic emergence of these nucleic acids. Not life, they told about this thing. So, so from these calculations, it is almost inevitable that RNA has more best bound, so they are more uh, uh, they are more suitable as a replicator. So let us discuss something about bacterial cell division also. So as we are talking about self-replicator, so bacterial cell division also involves these things. You can see from the figure that the bacterial cells are replicating in a very fast environment, in very quick environment, quickly. So there is some sorts of division time also. For example, in a certain time, they are going to become twice of their population than these and that. So there is a mathematical modeling. As in our previous lectures also, Dr. Devasi sir has modeled something. So the question is, what is the minimum amount of heat a bacterium needs to generate during the replication process? This is the question. How efficient is the process? mean, is the process of bacterial replication is 100% or less than that? And what are the reactions associated with the replication? Because the reactions are the most important thing. Ultimately, they are the thing which are generating heat and all these things. So we have taken a large system containing a E. coli bacteria immersed in a sample of rich nutrient media in contact with a heat bath held at a bacterial cell's optical growth temperature. So whoever are interested in biology, in either also many students who work on bacteria, so they grow bacteria in some petri dish and very suitable environment. You have to give a very suitable environment for growth. Otherwise, they will not grow. Sometimes they decay also. So this is a growth. This is state one, and this is state two. Okay. So the single bacteria is going and becoming two, three, four, five as time progresses. So the cell is in exponential growth phase at the beginning of its division cycle. So the process is highly Boltzmann, a non-Boltzmann distribution. Okay, non-equilibrium process you can say. So we have taken that. Maybe let us suppose the duration of single round of growth and cell division is tau division. We have supposed it. So 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 for the process of bacterial cell division introduced above, our ensemble second is a path of nutrient-rich media containing bacterial cells in exponential growth phase at the start of their division cycle. So in order to make use of the relation of the extended law of thermodynamics, as we have before also we had used it, we need to estimate this one, the probability of going from second to first. So this is our that extended law of thermodynamics, and we have calculated this portion. So similarly, we have to estimate the ratio of the probability of irreverse backward to forward trajectory. So thus, we will end up in an arrangement where only one and newly formed bacteria is present in the system, and another cell has somehow been converted back into the food from which it was built. If we consider the backward arrangement, then we will be left with single cell. For example, there are two cells in one division cycle. Then, if we reverse back to it, then there will be single cell only. So, what is the probability of that? So, in order to make up a model for the probability of a bacterium disintegrating over a set of period of time, we need to specify the period it starts to disintegrate, and here two different factors collide. So there are two different factors in order to calculate the probability of a bacterium disintegrating backward. So this is a hydrolysis of a peptide bond. So this type of reactions happening. Okay. So the less time we wait for the disintegration to begin, the less probable it is that it will happen in that period of time. And the longer we wait, the more new peptide bonds will get synthesized in the normal course of growth, so that the probability of subsequently undergoing spontaneous degradation of the whole cell in the remainder of the time tau division shrink exponentially. Okay, so there are two factors which are playing, one disintegration and one is integration. Means a synthesis of bonds and disintegration of bonds, both are playing a role. So now we have to choose a time. Okay, so the next point is between these two countervailing effects, there must be an optimal time that maximizes the probability of disintegration. There should be a time. Okay, so now let us take it more mathematically. That growth happening at a rate of n peptide by tau division. There are n pep by a number of bonds, and tau division is the time of first cell division. So if you divide it, you will get the rate of peptide bonds formation. Similarly, disintegration, hydrolysis of peptide bonds happening at a rate of probability rate 1 inverse tau hydration. Thus, the total cell hydrolysis probability in time t is modeled as. So, this is a simple modeling of the hydrolysis probability. Okay. And now what we did, we maximized it, we differentiated it and calculated the Tmax. As before, we need to optimize the time where the rate of hydrolysis will be maximum. So what we did, we differentiated this term and we have calculated Tmax and put back into these equations. So we have found the optimal maximum tau hydration probability. Okay, so now we have calculated the backward trajectory going back from 2 to 1. So this is the probability which is coming. Okay, so now we are putting the same thing into the second extended law of thermodynamics, and this is that our irreversible term, and this is our internal entropy change. Okay, and this is our heat bound. So this relation demonstrates that the heat evolved in the course of the cell, making a copy of itself, is set by decrease in entropy required to arrange molecular components of the surrounding into a new organism. First, heat bound depends upon the internal entropy change. Okay, and second thing is this tau division. How rapidly this takes place, how rapidly the cell division is taking place. That is also very important parameter to calculate the heat bound. To which is very responsible for heat bound. And the second thing is that how long we have to wait for the newly assembled structure to start falling apart. 2 minutes. So there are three parameters which are governing the heat bound evolved in the course of cell making copy of itself. Now, the contribution of the irreversible term. We have calculated the irreversible term. So what is its contribution is in comparison to other terms. So we have put the tau division as 20 minutes because at every 20 minutes, one cell is between two. And the Tmax we have calculated coming as 1 minute. So this equation in terms of number of pi bonds is 42 n peptides. But the entropy change is only 10 n peptides. So we can say that the main contribution for the heat exhaust is coming from the irreversibility of the self-replication reaction and not from the internal entropy change. So this term, the irreversibility term, is playing a fundamental more main role in the heat which is exhausting from the cell. So E. coli replicate close to thermodynamic limits of efficiency. E. coli bacteria is replicating at the level of thermodynamic efficiency. Okay, so we can say that E. coli produces at most 6 times more heat than they need to meet the constant of second law of thermodynamics. So, for example, if they need to meet the constant of second law of thermodynamics, just 10 joule. But what they are doing, they are producing more 6 times more, 60 joules. Okay, so they are very easily uh, validating the second law of thermodynamics by producing more heat. And thus, the replication of E. coli bacteria is close to maximum efficiency. They are almost maximum replicating at maximum efficiency. So now, as a summary, I would like to tell that the cost of making life is more dominated by irreversibility than by order. People used to say that in life, what happened, there is an order, and to make the order, the entropy has to reduce. But here, what is happening? The cost of making life, you can say in terms of as we define life, we don't even know what is life. But cost of making life is more dominated by irreversibility. More irreversible your reaction is, more heat will be produced, and that heat would manage the cost of generating uh, life. You can say. Second law of thermodynamics is not violated by life but used to provide the heat bounds for the replication. And the Darwin fitness is made more mathematical using thermodynamic approach. Initially, Darwin QE has been vaguely termed as the fitness, these are by observation. But here somehow some mathematics has been included to uh, tell that there is more refinement to Darwinism. So these are some of the references which I have used to understand, have read some, given a lot of time to understand these things. Okay. So if anybody interested, you can read these papers. It's very nice and very amazing work. And lastly, I would like to say that still to this modeling, there is a lot more thing to be done in this modeling thing because it's still under a lot of refining process. And yeah, so we cannot take it as final because a lot of new changes is coming to these theories and all these things. So a very nice book. I have read this book some time back, Biological Physics. It tells about energy, information, and life. So anybody interested can read this book. So thank you all, and yeah. So
Thank you, Mr. Roshan Tiwari, for your presentation. Now we'd like to open up questions from the participants. Maybe we could you could raise your, see whose hands are raised. Okay, we have Niket Kumarja. Maybe you'd like to unmute yourself, and maybe have the spotlight on the speaker. Thank you.
Yes, sir.
yeah,
Yes, sir. So given this equation, that means growth rate minus death rate, like Pn of t is Gn into Pn minus Pn of t plus minus Pn of t minus generation, means generation rate minus death rate you have given. So what is, how much is the difference between generation and that death rate? Can you elaborate
uh, there
how
is a
much
I
is the
yeah I
difference
didn't.
and parent?
Yeah, because this cell division is a very efficient process and it happens because of that. It's a irreversible process, but somehow the bound, you can say, I can say that the you can see the single cell division is happening after 20 minutes, but for breaking about there are in a single cell, somehow there are billions of peptide bonds. So in order to break it, it will take 600 years. Okay, 600 years. So there is a huge gap. So we have already seen that the process will not go reverse. Any two bacteria will not become one. Okay, so it will take time. Okay, so there is a huge gap between that. Okay, so the researcher who has did this work has taken the backward reaction to calculate the bound on the heating. How much bound, how much heat is producing. He has taken the backward reaction as a tool to calculate the bound. Okay, if you need more discussions, I will share you the paper and then we can discuss more. Okay.
Okay, thank you,
So
Niket.
you mean to say that this for reversible process?
What? Can you
Yes,
repeat?
sir.
Please repeat.
To say that this entropy has to be very high for this reversible process to happen. I mean,
Yeah.
very high entropy in positive value it is for reversible process you meant.
Yeah. For every
Means how
reversible
is it reduced? Like how, what is the experiment in that reducing the entropy for
entropy
this
cannot be
reversible
reduced.
process?
Entropy cannot be
Yes,
reduced.
sir.
Okay. First of all, entropy cannot be reduced. We what we see. For example, I have given examples of a plant growing forward. Okay. Okay, it seems that they are they are creating more order, but if you take as a whole picture, if you include the total system, for example surrounding also, then we can already see that it's obeying second law of thermodynamics. So you have to include the entire system. You have to include the system plus surrounding. What we see, we just see a very narrow picture that, oh, the heat is generating from this thing, but where it is dissipating, that heat you have to also take into account. So that will make the second law getting validating for every living system. Okay, so no system will ever uh, um, uh, means not follow second law of thermodynamics, but somehow in quantum systems, some new researches are coming where they are showing that some quantum systems are not obeying these that. So there are a lot of mystery, and you can see it, can learn about more.
Thank you so much for your question and your answer. We have our next question from Saumya Deep Das. Can you please unmute yourself?
Um, am I audible?
Yeah.
Yes, clearly.
Yeah. Um, Hi, Roshan Bhaiya. Yeah,
Yeah,
it's
yeah.
Shomodip from DBS Aizer Kolkata.
Okay.
So, your junior. Yeah. So, from your talk, uh, if I am not wrong, it can be concluded that irreversibility is more important than
Yes.
entropy. But in some popular cases, even in the fan fictions like the Dan Brown's book named Origin, uh, it is mentioned that for the origin of life, entropy is more important. So can I guess that for origin of life, the fundamentally more important aspect is presence of entropy and spontaneity, and for maintenance of life, as you mentioned, for growth, reproduction, and metabolism, the more fundamental or better idea is the irreversibility.
No, first of all, the irreversibility is connected to entropy production. Okay, it's not a different two different terms. First of all, the more irreversible the process is, the more entropy change, the more entropy change of the surrounding will happen. More entropy production will happen. So the heat which is dissipated in the surrounding is connected to entropy. Okay.
Okay, so but the equation you are mentioning, so it considered the internal entropy, if
Yeah, yeah.
I'm not
Internal
wrong.
entropy. Yeah, yeah, yeah. So
Okay,
internal
okay.
entropy of a system. Okay.
Hmm.
So that is also very important part. So that is defining the order of a system. So
Okay,
the
yeah, yeah,
order
yeah.
of order of a system is dependent on the entropy change of the system.
Okay, yeah. Thank you, Bhaiya.
Mm.
Thank you. Are there any other questions for Mr. Roshan Tiwari? Okay, I see Naked Kumar's hand again. Naked, okay, can you unmute yourself, please?
Mm, yes, sir. Sir, you have told that time reversal symmetry, nature tries to bring back itself. But don't you think that this somehow means reversible process is actually happening all around? Like living organisms also try to mutate themselves, adapt themselves, and they try to bring back themselves so that they can put up themselves in the environment in a better way with habitat changes also.
So,
So,
so I
like
got you.
the energy itself is coming back in the nature also. Like you gave the plant example that plant itself is decomposing, then it is means producing more plants. So in that way, nature adapting and doing things like
So what is reversible process?
this
For first you
way.
need to understand
So
it.
how is it
So
related to life then?
for example, yeah, for example, in reversible process,
Yes,
as you told that every process which you see are mostly irreversible. For example, I have given an example of rusting also, the oxidation reaction,
yes, sir.
the burning also. This is irreversible process. A burn wood cannot turn back into a thing. And as per your question, you are saying that even the evolution happens and adaptation happens. That also doesn't, it's not isolated. It involves a lot of heat exchange between the system and surrounding. And they are driven by some external agent. So whatever non-equilibrium process, what I told was, if you have some external driving, okay, that what it will do, it will deviate the reaction, it will deviate the process from equilibrium to non-equilibrium. So non-equilibrium process and this irreversible process are happening everywhere. Some reactions are reversible. For example, the reaction between N2 plus O2 forms NO. Okay, then NO and the concentration of NO and the concentration of product and reactants are not varying with time. So they are in a reversible process. Okay, they are exchanging this and that. Okay, but for example, hemoglobin, we take oxygen, okay, oxygen, and then it binds with hemoglobin. Okay, it doesn't happen that oxygen released from hemoglobin, just oxygen coming out from it. It releases in the cell. So there are many reactions. You just note down all these reactions. Many reactions are irreversible in nature. Okay. So
Yes,
I what I found, like many reactions, like 99% reactions, 98% irreversible. So it's a basic question. It is basic, very good that
yes.
you are asking such questions. Very nice questions, and just make note down of
Because
all these
like I
questions.
think that nature is trying to, yes, because I think that nature is trying to do some adaptations. That's why so many processes we see are irreversible, so that some changes can happen and it can bring back.
So
So
that
like
adaptation is that
this is
adaptation.
some related to the origin of life, I think.
That adaptation is happening because of
Yes, sir, you were.
some external agent is also working now. Some atmosphere is changing. So So this adaptation is a very important part of nature also, even living being also. Okay.
Thank you.
So yeah,
Thank you, Nikit, for your question, and thank you, Mr. Roshan Tiwari.
Okay,
Maybe
thank
I
you,
have
sir.
one question. Can I ask you, in terms of if you could summarize the difference between irreversibility in living systems versus non-living systems, how would you summarize that? Because, as you said, you noted that most changes are irreversible. So if you want to look at living systems and
yeah.
non-systems, what would be the difference in the irreversibility?
I will give you a simple example that ice and water. Ice becomes water when it is heated up, and water becomes ice when it is cold. But plant never, as if you take living being, living organism is very organized and very complex. But non-living thing, it may be complex, but in many reactions we find that non-living things like ice and water, they are going back, uh, reversing back and forth, and at a particular temperature also, these three, what we say, the triple point of water. In triple point of water, vapor phase, solid and liquid, they all these phases coexist at particular temperature. So that is because of simplicity. But in living beings, for example, in myself, so much reactions is happening. For example, so many biochemical reactions is happening. Okay, and yeah, so that could be a case. And other thing is that equilibrium phenomena, as we have learned about Le Chatelier principle in chemistry, many people would have learned that is, if some process is undergoing and if some parameter is tuned, then in order to uh, uh, facilitate the reaction go back, something like that. So also need to wrap up my concepts more. So I think there is some differences between living and non-living thing, and this is because of complexity of living being, that irreversibility term is more fundamental to it. And yeah, yeah, for example, as you have, sir, asked that this second law of thermodynamics is universal to uh, all the burn, for example, burning. A wood is burning and converting into SS. Now SS cannot convert back. Similarly, there are reactions in our body which cannot come back. So there is some sorts of mapping between living and non-living thing.
Okay, so there are similarities
There
definitely.
is similarity there.
I'm just wondering what the difference would be. Yeah.
Yeah, yeah. So as a body, as we have a meaning, we have a body. We have body consisting of carbon, nitrogen, all these atoms and all these things. So as per scientists now, they are researching on life and all these things. So still now they are still our we are looking for life in matter also. So as such, thermodynamics related to some matter and all these things studies. So that is we are doing as a scientist. So I think there is more to do research and all this.
So would open systems and closed systems be a
Yeah,
consideration in your research?
yeah, yeah, yeah.
Okay. Okay. Thank you. Thank you for your answer. Are there any other questions before we proceed to the next speaker?
So I
Anyone?
think Niket has a lot of question.
Okay, Nikit's got another question. Say, Nikit, please unmute yourself.
Yes, sir. Thank you for giving me chance. Like, can you explain? I did not understand that you related this reversibility rate with metabolic rate also. Like you told that as per Darwin theory, more metabolic rate has more chances of survival and adaptation to environment. But I see that like so many means general question that suns and like those people go to Himalayas and they do lot of hard work, like, and then polar bears also hibernate for so many 6 months to years also, like to 1 to 2 year they will go and hibernate. Similarly, tortoise also seen in nature have very long life of more than 100 years also, but they don't eat much. So means if means they may have somehow lower metabolic rate also in that case, then how is it that they are more adapted to the environment?
For example,
Yes, sir.
if you have a more growth rate, okay. So if, for example, if I eat more, for example, single cell, for example, consider if I have more metabolism rate, I eat more. So my capacity to reproduce will be more. I will reproduce more. Okay. So if I reproduce more, so in a single time I will have a more population. So the population, the large amount of population will be connected to the survival, isn't it? If I have a large population, then my survival would be better than other species which didn't survive, which didn't have much population. Okay, this is just a modeling of some sorts of some view, some aspect of things. And hibernation, about
Yes,
hibernation
sir.
also,
Like,
it's a very, yeah, it's a very nice question that, for example, if I decrease my metabolism, then the aging process, for example, in also our yogis, the aging process will reduce. Okay, the functionalities
yes,
of my cells working so hard will reduce. So these two things, I think we should not connect, because the first thing which I told was the related to population. If I have more metabolism, I will grow more. I have more population, then the chance of my survival of my species will be more. And if for example, if other species there which didn't reproduce, then
yes,
maybe it will lose for after some time.
yes, sir. You mean to say like we generally say that if we use more brains, we get sharper. Like this, if we eat more, then our metabolic rates and survival also increases in environment. Like this, you related, I think,
We cannot generalize
told
always, but
earlier.
yeah,
Like if
somehow
we,
if you eat more, maybe you will hospitalized.
yes, sir.
So it's not so for
Uh,
every. It's a single cell. This is a modeling of a single cell. It's not we have. It's not modeling for multicellular human beings, something like that. It has been simple model of single cell. Okay.
yes, sir. Yes, sir. Like in bacterial cell division model, also for the optimal media, you told that if we put proper environment condition for bacteria, then they can grow more and
Yes.
replicate also properly.
Mhm.
But the thing is, like in origin of life, like means billions of years ago, there was not proper condition. Like means it was so much heated up planet, then somehow it gets cold due to asteroids, water through ice. Like this, there was very unfavorable conditions. So means is it possible to relate like how then optimal media was obtained and what external conditions helped, like even in some small organisms like bacteria also for their initial growth phase, like how they
Niket,
survive even
It's
in
a very
unfavorable.
speculative questions. I do not want to comment because, as you know, we have already so much lectures. What we are seeing that it's a lot of speculations for origin of life. So I have no comments. So it would be you can go and search for
Ask for
yourself.
very
Okay.
Thank
like
you,
this
Niket,
small
for your question.
organism.
Thank you,
Yes, sir.
Niket.
Okay, thank you, sir, for your answering. And whatever, thank you.
Okay, maybe I just ask one quick question about yesterday Dr. Mukodapai said talked about asymmetry to symmetry, right? So when you talk about irreversibility, right, in are we moving? Are the systems moving towards equilibrium?
All every system moves towards equilibrium until and unless no external agents are there. If you apply always force, then how any system becomes equilibrium? You have to make it free. So even irreversible process also is making it to equilibrium. Everything is tending to equilibrium.
Okay. So whether reversible or irreversible processes
Yeah,
are.
yeah, yeah, yeah.
Okay, thank you for clarifying. Thank you so much, Mr. Roshan Tiwari.